In this paper, we propose MultiTalk, a method for task planning that aligns with the user's intentions, environment's constraints, and the executor's capabilities. We use multiple feedback sources via designed pathways to assist the planner in resolving task ambiguities and aligning the plan with environmental and executor restrictions. We illustrate our method through a task-guided robotic manipulation setup. The overall framework consists of 4 modules, exchanging information and feedback between them to generate a logical plan that is consistent with the robot's capabilities and environmental limitations. The perception module identifies and localizes all objects in the workspace by using a grounded SAM framework with depth information to generate the bounding box coordinates and labels of all the objects. The LLM-based planner is central to our method. It generates a sequence of action primitives based on the environment information. For tasks with ambiguities, it clarifies the user's intentions through direct active questioning. Notably, our LLM planner generates highly detailed, easily executable plans by providing coordinates instead of choosing from a predefined set of locations. The generated plans may have logical issues, hallucinations, or inconsistencies. Therefore, we feed another LLM instance with the same information, specifically prompted for fault finding and criticizing the planner's output. The analyzer reviews the plan, providing feedback and reasoning for each infeasible or incorrect action. Once the analyzer deems the plan feasible, it must be vetted for execution feasibility on the robotic manipulator. We implement a MuJoCo simulation of our setup to observe the robot's state variables and objects, testing for singularities, controller failures, and collisions. Detected errors are communicated to the planner for correction through natural language feedback. To show the iterative process in action, we present an example task of interchanging object locations. It starts with the perception, generating the object locations and bound. The planner acts upon the received object locations and task to generate the first plan. This plan is then perused by the analyzer for errors. The proposed plan places the sugar box directly in the location of the mustard bottle. This logical flaw is caught by the analyzer. The plan is updated using this feedback. This time, the plan is accepted by the analyzer and successfully passed to the simulator. The simulator notices that this temporary location falls in the singular space of the robot and provides appropriate feedback to correct this. The planner takes note of this and chooses a more accessible temporary location. The new plan is sequentially checked and approved by both the analyzer and simulator, giving us the final plan. After a final manual check by the user, this plan can be executed end-to-end on the robot. This is a proof of concept of our methodology and how multiple feedback loops could improve the accuracy of LLM-based planners. Sometimes, the perception system fails to detect some objects. Realizing the inconsistency between the detection and the task, the planner requests for a rescan from an alternate view in such cases. Thank you for taking the time to listen to our presentation.